BC students. Well, this is it. Last one of the year. Let's make it count. I'm not sure, I might post a little extra practice on Monday if you're interested. It's not required. This is pretty much it, though. And I hope to lay a little video and wish you luck. But if you don't check it, and this is the last you hear from me, I wish you the very best Tuesday. Just show up and do what you do. That's all I ask. I'm not a big speech maker. Just do what you have learned. You're ready. You're going to do great. Okay. So let's spend the time on the calculus, shall we? So here we go. Maybe I'll give you a little extra something at the end of this lesson. Let's go to notes first. Hopefully you printed this off. And Unit 9 is not on the test, but just looking at the big ideas that will not be on the test, but are big parts of Calc 2. Parametric equations, polar coordinates, and vector-valued functions. Especially parametric is built on, and vector-valued functions. They're built on a lot in Calc 3. They just go into 3 dimensions, but you need a good solid foundation in Calc 2. Topics of these to get on in Calc 3. So make sure that you review these big ideas. I'm going to spend about 2 minutes hitting some of the big ideas, and then we'll move on. So here we go. First, when you talk parametric equations, you talk position in 2 dimensions at time. We did a lot with this, eliminating the parameter and using a parameter and modeling motion down the hallway. None of that stuff would be on the test, even if this was on the test, but you would be expected to know that x of t and y of t give horizontal and vertical position. And if you did this in a vector format, it would be pretty much the same. You need to know that the velocity, whether it be a vector or not, was the change in position horizontally, the change in position vertically. The magnitude of the velocity, or how much velocity without direction, is the same as speed. And that is not a slope calculation. It's Pythagorean theorem kind of calculation, all right? And then obviously the acceleration vector is the second derivative of both. Okay. Also remember that integrating, just like in one-dimensional movement or linear movement, integrating speed gives distance. Integrating arc length or integrating speed gives you arc length or distance in 2 dimensions. All right. Second derivative, remember that usually the first derivative is in t terms, so that when you take the derivative again to get the second derivative, you'll use implicit, and you'll usually be dividing by dx dt because of that. All right. Integrating vector-valued functions, you could get, if you had velocity vector, you could get position by integrating x and t, x and y. Right? To get both vertical and horizontal position. Solving problems, so many problems. You get angles of entry and all that good stuff. We've done a lot. Polar coordinates, remember the idea at very heart is you could get directions by either going horizontally and vertically or traveling out so much at a certain angle. R is defined as the distance from the origin. So dr d theta is how the distance from the origin is changing, or whether the thing is moving towards the origin away. X is r cosine theta. It's a shame this won't be on the test because you guys are absolutely killer at this. You guys are great at this. And the slope of a polar curve can be found by taking dy d theta over dx d theta. Okay, and then area is 1/2 of the integral of r squared with respect to theta, and we use symmetry all the time, and area between curves and all that great stuff we learned. All right, so I didn't give any practice on that. Instead, I focused on practice on series and general mixtures, which is what you'll see. So let's talk series. As far as these ideas that'll be on the test, geometric is on the test, harmonic, alternating series or conditional convergence test, ratio test, and general Taylor series approximations of functions. Now those are on the test. These are yes. Okay, so geometric, is when you are multiplying by a common ratio. So when you see something to the n and it's only x or a constant, otherwise no n factorial, nothing else, then that's geometric. The idea being that whatever the first term might be, in this case it's 1, but what you multiply by each time is r. So this is the power series form of the geometric, but it could just be numerical geometric, all right? It must be the case that the r is between -1 and 1 to converge, not inclusive. Alternating series test for convergence. Remember, if a series is alternating, the terms decrease to 0, go to 0 and decrease, or there is a point at which they decrease forevermore, then it converges conditionally and therefore converges. The ratio test for convergence, remember, is the idea of comparing the next term to the one before it and looking at the limit. If L is less than 1, then converge. If L is greater than 1, diverge. L equals 1 is inconclusive. Do some other investigation. And then finally, Taylor, gosh, it's so big, but let's just go with the big idea. A series or sum of polynomial terms can approximate a function by matching that function at the point, the derivative at the point. 1 factorial, and generally all derivatives at the point. Yeah. Okay, so let's practice, shall we? Let's start with this series problem. Take 15 minutes to do the series problem and we'll check your work. Okay, so let's see how you did. The first one is basically a development. So in essence, G is the series you're going to get by putting x squared in for each. It looks like that's sine, right? Am I wrong there? But you're right, x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial, which would obviously be x to the 10th, minus x squared to the 7th, which would be x to the 14th over 7 factorial, and -1 to the n, x squared to the 2n plus 1 over 2n plus 1 factorial. So in essence, do you know how to do substitution into a series? A rookie would think, oh, God, I got to do all these derivatives. No, that's not the case. All right. If you simplify those, you can see that they're all going to go up by 4 each time. And if you wanted to simplify, that's fine. It might help for the next problem. But so the next problem, I went off in one direction and decided this is not going well, and I had to change. So if you're like me, You might have thought, man, do I need to do 10 levels of L'Hopital? And the answer is no. You can get to the answer of 1 over 5 factorial. If you remember, one of the big skills of L'Hopital that keeps you from having to do it multiple times is simplify as you go. All right, so instead, let's go with this. I think you'll agree that if you take x squared minus x to the 6th over 6 and subtract away g to the x, then these guys will subtract away, and you'll have the opposite of all these. So you'll have negative x to the 10th. Maybe it should be negative. Yeah, this should be negative 1 over 5 factorial, sorry. Negative x to the 10th over 5 factorial plus, remember I'm subtracting g, so I'm changing these signs after these guys drop away. So this will be minus, this will be plus. X to the 14th over 7 factorial, and eventually I guess you'd have a opposite of negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. Now all that's great, but that's not an issue because I'm going to divide by x to the 10th. Now if I divide by x to the 10th each term, which I can do, then I get negative 1 over 5 factorial, x to the 4th over 7 factorial, and all terms after that would have an x minus 8 over 2n plus 1 factorial. And so because they all have a x and x goes to 0, you would just approach negative 1 over 5 factorial. Right? Part C, I have 13 over 42. If you have that and you feel confident in your work, cool, move on. If you don't have that, then let's talk about it here. And let's go. So I'm going to say that h is the antiderivative of g, and therefore the series for g. So the series for g, but using t instead, is t squared minus t to the 6th over 3 factorial plus t to the 10th over 5 factorial minus t to the 14th over 7 factorial. Gradually, generally to negative 1 to the n, t to the 4n plus 2 over 2n plus 1 factorial and beyond. If I integrate that, I get t cubed over 3 minus t to the 7th over 7 times 3 factorial plus t to the 11th over 11 times 5 factorial minus t to the 15th over 15 times 7 factorial. And generally speaking, negative 1 to the n, t to the 4n plus 2 plus 1, so 4n plus 3, divided by that new 4n plus 3 times 2n plus 1 factorial, evaluated from 0 to x. When I throw in x, I get x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial, and so on. Therefore, h, I didn't ever finish. I guess I got to do that. Doggone it. Negative 1 to the n, x to the 4n plus 3. Don't get lazy, Corey. 4n plus 3, 2n plus 1 factorial, and beyond. Therefore, h at 1, using the first two terms, would be 1/3 minus 1 over 7 times 3 factorial, which is 1 over 7 times 6. 1/3 minus 1/42 is 14 42nds minus 1/42, which is 13 42nds. All right, and last but not least, part D. So it's alternating series error bound. You did not have to use Lagrange. It's alternating. So I started by justifying alternating the series. H1 series is alternating. The terms go to 0 and decrease. So it is the case that the true H at 1, which is exact, and my estimate of 13 42nds is like the difference between the true infinite sum and the sum of two terms, which is less than or equal to A3. A3 would be the next term in the series with a 1 in for x, which is 1 over 11 times 5 factorial. That's 1 over 11 times 120, which is 1 over, let's see, that's 1200 plus 120, so 1320, and that is less than 1,000. All right, so there you go. Try the next one, 15 minutes or less, and we'll check your answers. Okay, let's see how you did. For A, I have an answer of negative 1/7. If you agree with that, then you're probably good to go. B, I have this gross y plus 3 equals negative 1 plus 3 pi over 2 x minus 3 for my tangent line. Seems kind of gross. It always feels funky when something's that gross, but it is what it is. The average value here I have is 9 pi over 28 minus 8/7. And the last, I used the extreme value theorem to prove, yes, it must have an absolute max because it satisfies the conditions of the extreme value theorem, which is continuity on a closed interval. All right, so whatever you need to make corrections on, let's do it. Let's also focus on good calculus because we have a piecewise here. All right, so the average rate of change, remember, differentiate between average value and average rate of change. Average rate of change is the change in f over the interval. F at 4, I use the upper or lower function. And I got something like negative 4 plus 3 cosine of 2 pi, which is negative 1. And for f at negative 3, I used the upper function, 9 minus 9, which is 0. So I got negative 4 plus 3 minus 0, and that's negative 1 over 7. That's where I got my answer. All right. B, you need a point and a slope, and then point slope. The point is when x equals 3, f at 3 is the bottom function, so that's negative 3 plus 3 cosine of 3 pi over 2, which is just negative 3. So the point I'm working with is 3, negative 3. The slope is the derivative at 3. The derivative of the cosine function is negative 1 minus 3 sine of pi x over 2 times the inside derivative of pi over 2, evaluated at 3. So I got negative 1 minus 3. Sine of 3 pi over 2 is negative 1 times pi over 2. And so I got negative 1 plus 3 pi over 2 for the slope, and then I wrote my tangent line. All right, C was the hardest one. Heavy on technique, which is definitely a strong suit for you all. You have excellent integration technique. Show your work well. Anytime you do piecewise, you have to show you're using which piece at a certain time, right? That's just good calculus. So it is very common that even students of your caliber will do this. They'll say, well, I'll do the average value on the first piece and then the average value, on the second piece. And that is 100% wrong. That is not right. It is the average value of the whole thing. And as far as the piecewise, it occurs on this, not this. This, you're taking the averages of the average value, or the sum of the average value. You're going to get some y value that's above all values. That's ridiculous. You don't sum the average values. That's crazy talk, all right? So instead, it's 1/7 of an integral from negative 3 to 0 of the root of 9 minus x squared, which I beg you, please don't use trig sum on that. Use geometry, and 0 to 4 of negative x plus 3 cosine pi x over 2. Also, don't do your calculus all at an angle like this. What's that about? All right. So 1/7 of this. I think you'll agree that positive root is a half circle. Negative 3 to 0 is just the upper left, so it's a quarter circle. Pi times 3 squared over 4 for the first integral. The next integral, whether you use subdet or not, is up to you. But you best obviously be careful with this. You better treat that with care. And if you did use subdet off to the side, I would probably go off to the side if I did this, rather than do it in the context of this really big mess, and say, hey, here's what I'm doing, person reading this. I let u equal pi x over 2. du is pi over 2 dx. So 2 over pi du equals dx. So I get cosine of u times 2 over pi du, the antiderivative of which is 2 over pi sine u. And then sub back to get 6 over pi sine pi x over 2 from 0 to 4. If I evaluate, I get 1/7 times 9 pi over 4. When I put 4 into the antiderivative, I get negative 16/2, so that's negative 8, plus 6 pi sine of 2 pi, which is 0. When 0 goes in, I get 0, and sine of 0, which is 0. And so 1/7 of that is 9 pi over 28 minus 8/7. And that's where I got my answer. Boom. All right, last but not least, one of the skills they expect you to demonstrate in AP calculus is to prove you can apply theorems. You know how to work with theorems. First, you need to know the theorems you're expected to know. Second, you need to meet the conditions and then apply the theorems. Now, the idea here that they're getting at, small mini lesson, is if a function is allowed to go forever, oops, my bad. If a function is allowed to go forever, it's possible it won't have an absolute max, all right? Now, a parabola has an absolute min, though it's allowed to go forever. It's just endpoints help it considerably in that it terminates the possible infiniteness on the outsides. However, that said, if you think about a graph like this has endpoints, but it doesn't have absolute max and min because, again, it's got that infinite discontinuity. But if you put those two things out of the picture, closed interval and continuity, if I start at a point, never lift my pencil so it's continuous, and end at a point, there's no possible way to draw a graph without an absolute max and min. So the original first part of the extreme value theorem is if a function is continuous on a closed interval, it must have an absolute max and min. And then we often use how to find those, which is critical numbers and endpoints. But the first part is, when are you guaranteed to have one? That's the part you need here. All right. So the extreme value theorem states if a function is continuous on a closed interval, it must have absolute max in this case. I hope your handwriting is better than this on the AP test. Well, I can see it has endpoints. That's good. Now the question is it continuous? So that's what I want to get into and prove. All right, remember for continuity, the limit from the left, which is 3, and the limit from the right, pi x over 2. Let's see, we got negative 0 plus 3 cosine of 0 is 3. The limit from the left and the right must be the same, so that the limit exists, and it equals 3. The point must be defined. F at 3 is defined. It's one of the branches, and it equals 3. And therefore, because 3 equals 3, F is continuous at 3 and at all interior points. And so, and all other points, other x in negative 3 to 4, because each of those branches is continuous. So we can conclude that because the function is continuous on a closed interval, by EBT, there must be an absolute max. All right? That one was rough. All right, last one. Here we go. Take 15 minutes to try this. You do not need a calculator, use Sissy, and go, and I'll talk to you on the other side. Okay, here we go. For this, did you get 40.2 for the first? I did. I hope that's right. For B, it was more of a proof, but I got F at 6 must be less than 62. Really a cool proof, elegant you would call it. And it was fun, and that was a really cool problem. I enjoyed that thoroughly. Number C, also known as letter C, was negative 0.3. And I gave you way too much space for the work there. It didn't require that much space, sorry. And then for the last one, I got negative 8. All right, so either focus on these and watch these or fast forward to a little video clip at the end if you have all these right. Here we go. Let's go. All right. Oh, goodness. All right, here we go. Oh, dang it. Just stop. All right, so let's talk about this. Approximating f at 6. First thing you had to start with is fundamental theorem. This is an f prime graph. So by fundamental theorem, f at 6 would be f at 0 plus the change from 0 to 6. And the change is the accumulation of lots of rates of change times amounts of change in x. Looks like Euler. This is cool. Okay, so that can be approximated by a Riemann sum. So f at 0 is what it is. That's not the approximation part, but the others are midpoint rectangles. So I took the first interval from 2 to 0 and then multiplied by the midpoint, f at 1, plus from 4 to 2 times the midpoint height, f at 3, plus the last interval, 6 to 4, times the height at the midpoint, f at 5. That's 20 plus 2 times 3.5 plus 2 times 0.8 plus 2 times 5.8. And that's where I got 40.2. Now, if you got 20.2, you just focused on the integral. You just didn't read and said, oh, midpoint Riemann sum, boom, integral, here I go. And you didn't look at the whole context of the problem, right? So you left out that, and that's kind of important. All right, moving on. How did B go? I really liked B. It was fun. It's one of those where you feel an accomplishment, sense of accomplishment when you get it, and you see where they're coming from. Come on. All right, so I started by saying, geez, sorry. All right, I started by saying that I was given f. So I actually started by saying, what is f at 6 even going to come from? Well, I know from previous that f at 6 comes from f at 0 plus the change from 0 to 6, yeah? So I'm thinking, well, why would that be? Why couldn't it be 70? Sure, why not? Well, are there restrictions on this? And yeah, given there's a restriction on f prime, and given that there's a restriction on f prime, there's a restriction on how much f can grow, or how fast f can grow, and therefore how much it can grow, and therefore how much it could be. So the question then is, all right, so how do I start with that restriction and work out? Well, that's exactly what you're going to do. Start with the fact that f prime is always between 0 and 7 as given. And you're going to build out to this and hope that it gets you somewhere. So when I build out to this, let's start by integrating. Now, if I integrate all three pieces from 0 to 6 with respect to t, x, t, what the heck? 0 to x, f prime, 0 to 6. Jeez, getting tired here. 6, 0 to 6. All right. And then I'm going to add in f at 0. So f at 0 added to all three pieces. If I add the same thing to all three. That's cool. Okay, so I'm going to add f at 0 to each piece. Now I've got the expression I want to bound now in the middle. Now I just need to figure out what are the bounds on the other side of this, yeah? Now I know that f at 0 is 20, and the integral is 0 there. So that means that f at 6 has to be at least 20. This is f at 6. And now let's focus on the other side, because that's where we're going to get some stuff. 20 plus the antiderivative of 7 is 7x. From 0 to 6, that should be. All right. So f at 6 must be greater than or equal to 20 and less than or equal to 20 plus 42, or 62. Now that's less than 70. So from that I can conclude that f cannot equal 70, because it must be less than 62. All right? Wasn't that cool? Okay. This one is just straight up fundamental theorem. C is. So the fundamental theorem of calculus on the most straightforward level is to do a definite integral. You take the antiderivative of f double is f prime, and evaluate it at the upper limit, subtract away the lower limit. So this is equivalent to f prime at 4 minus f prime at 2. And from the table, that is 1.7 minus 2, and that's where I get negative 0.3. All right? And finally, C, D. All right, here we go. I first am in the habit of just doing a mental estimate on this, because every time I see one of these, I think it's probably L'Hopital. And I think you'll agree that because f at 0 is 20, as given, you get 20 minus 20 to the 0, so the top is 0. Half of 20 is 10, minus 10, bottom is 0, so by L'Hopital. So I'm feeling L'Hopital, so here's quality work. The limit as x goes to 0 of f of x minus 20 e to the x is 0. The limit as x goes to 0 of 0.5 f of x minus 10 is 0. So by L'Hopital, this is equivalent to the limit as x goes to 0 of f prime of x minus 20 e to the x over 0.5 f prime of x minus 0. Alrighty, eventually. Now at 0, f prime at 0, according to the table, is 4. 20e to the 0 is 20. And 0 half of 4. So I get negative 16 over 2, and that is negative 8. All right, so that's it. I hope you drop by my website, my calendar, or Google Classroom for either extra practice if you want it, or just for a little good luck on Tuesday. But hey, have a good weekend. Stay tuned.
Hey, wake up, wake up. You remember me, Mr. Rickman. The tougher Mr. Rickman, you remember. Hey, I heard you guys are taking your AP test next week, and so I had to try to take over one last time. Last time I had you guys doing some artwork to give you guys a break from, Snoozy McSnoozerSon's class. This time, I know that going into the AP test, it's important for you to have the right mindset. And I'm sure that some of you guys are anxious and nervous, but having my brother all year long as your teacher, I know that leaves you with a bunch of pent-up frustration, anger, confusion. So I wanted to give you guys a way to get all of that out in kind of a fun way. So here's what I did. I designed a game for you. That way you can play this game, get some of that frustration out, put yourself in the right mindset for the AP test next week. And so here's what I want you to do. If you have your phone with you, what you're going to do is you're going to pause me and you're going to scan this. Now, if you don't have your phone with you, that's no big deal. Just go back out to the calendar where you found the link for this video, and I asked my brother to put the link to the game right in that description as well. So if you don't have your phone, pause me, click on that link, go ahead and play that game. All right, hopefully you had a good time playing Angry Weasels and getting some of that frustration out from having my brother as a teacher all year long and knocking some of that stuff down. Anyway, I'm gonna try to talk to my brother and make sure that he's classy enough to maybe give the top 3 angriest weasels on the leaderboard some kind of extra credit or something, but I'll work on that for you. So I made something else for you too, because a takeover of my brother's classroom wouldn't be complete without some way of telling him that I took it over. So here's what I did. I created a Snapchat filter specific to you guys, Devlin Calculus class. So here's what I want you to do. For those of you who have your phone, and if you have Snapchat downloaded, go ahead and pause me, and I'm going to have you scan a code. And what I want you to do is I want you to play with it a little bit. I hid a few secret things in there. If you open your mouth, something happens. And if you get your hand into the shot, I put a little hidden piece in there as well for you. But what I want you to do is take a screenshot of it and email it to my brother and let him know what you really think of it. Okay? So if you have your phone, you have Snapchat, go ahead and pause and scan this code right here. All right, I can't wait to see some of those pictures that you send my brother. Anyway, I'll let you guys get back to your snooze fest. It's your very last snooze fest though. So that's pretty exciting. I'll leave you with this. You know, my brother may be a lot of things. He may be a doof, he may be a terrible dresser, a weakling, a terrible singer, smells a little funny, but there is one thing that I know he's very, very good at, and that is teaching calculus. So I have no doubt that you guys are so prepared for this test and that you guys will kill it. Good luck. You guys are ready. You will be amazing. He is really proud of you guys, so do him proud next Tuesday, okay? Good luck, you guys. You'll do great, and don't forget.
You can do it! You can do it! You can do it! You can do it! You can do it!